Hey guys, welcome back to the channel. Today we are kicking off a brand new series on basic building blocks of programming, data structures. We are starting with lists in Python, flexible, ordered collection that lets you store numbers, strings, or even a mix. Up next, let's walk through a quick summary before we dig deeper into this awesome concept. A list is a built-in data structure in Python used to store an ordered collection of items. It's mutable, meaning you can change, add, or remove elements after creation. Lists are defined using square brackets, like 1, 2, 3 as you see. They can hold anything, numbers, strings, floats, or even other lists. Accessing an item by index is very fast, taking constant time O of 1. But inserting or deleting items, especially in the middle or beginning, is slower, around O of n time. Now that we understand the basics, let's dive into some commonly used functions and operations on Python lists. Here's our first topic, creating and accessing lists. Let's start by creating a list of first 5 odd numbers. We define it using square brackets and assign it to a variable called odd numbers. The list now holds 1, 3, 5, 7 and 9. Now let's look at how to access elements from our list. To get the first element, we use index 0. This gives us 1. As lists are 0 indexed, that is elements are numbered from 0 to n minus 1. To get the last element, we use index minus 1. This returns 9. So square brackets let us retrieve specific items based on their position. Next, let's access a portion of the list using slicing. To get the first 3 elements, we use list slicing start to 3. This gives us 1, 3 and 5. To get the last 3 elements, we use the same approach minus 3 to end. This returns 5, 7 and 9. List slicing allows us to extract sublists using a start and end index. Now let's explore how to add elements to a list. To add 11 at the end of the list, we use append method. Odd numbers.append 11. This adds the new element to the end of the list. Now the list becomes 1, 3, 5, 7, 9 and 11. Let's look at how to combine lists. Using the plus operator, we can concatenate another list to create a new list. To add elements to the existing list, we use the extend method. Odd numbers.extend elements, and elements are added to the end of the list, as you see on the screen. Next, let's insert an element at a specific position in the list. To insert 99 and put at index 2, we use insert method. Odd numbers.insert. This places 99 between 3 and 5, and the list is adjusted accordingly. Now, let's see how to remove elements from a list. To remove item 99, we use remove method. Odd numbers.remove. It deletes the first occurrence of the specified value. As you see, it has been removed from index 2 in the list on the screen. Now, let's use the pop method to remove elements by position. Calling odd numbers.pop removes the last element, which is 17, as you see on the screen. Next, odd numbers.pop with index 1 removes the item which is at index 1, that is 3. As the elements are removed, the list shifts to fill the gaps. Watch how the items slide into place as we pop them off. And finally, the updated list is 1, 5, 7, 9, 11, 13 and 15. Finally, to remove all elements from the list at once, we use clear method. This empties the entire list, leaving us with an empty set of brackets. Now odd numbers is simply an empty list. As you see, all items disappear in one go. Now, let's move on to modifying elements in a list. We start by creating a list called nums with some values. To update a specific item, we use its index with the assignment operator. Nums2 equals to 3 replaces 33 with 3 at index 2. The list is 1, 2, 3, 4, 5, 6, 7. This shows how lists allow direct updates using their index. Next, let's see how to replace a slice of elements in a list. Here, nums2 to 5 equals to 30, 40, 50 replaces the elements at index 2, 3 and 4. 3, 4, 5 are replaced with 30, 40, 50. This shows how slicing can modify multiple items at once. Now, let's see how to remove a slice from the list using slicing. By assigning an empty list to slice, we remove the elements at index 2, 3 and 4. That is 30, 40 and 50 are deleted. This is a quick way to delete multiple items in one step. Finally, we can also clear the entire list using slice assignment. By setting slice equals to empty list, we remove all items from the list. This is similar to using a clear method. Now nums is an empty list. It's another way to wipe out all the elements at once. Now, let's talk about copying and references in Python lists. We start by creating a list called original list and then assign it to alias list. This doesn't create a new list. Both variables now point to the same list in the memory. So when we append 44 to the alias list, it also shows up in the original list. This is called reference assignment, where changes affect both the lists, as you can see on the screen. To avoid unintentional changes, we can create a shallow copy of the list. Here, duplicate makes a new copy with same values. Now modifying duplicate won't affect the original list. We updated the last item in duplicate to 99. Duplicate becomes 12399 while original list stays unchanged 12344. This is useful when you want to work with a separate copy of the list. Another way to create a shallow copy is by using a copy method. Here new copy makes a separate list with the same elements. When we compare their IDs, it returns false. This confirms that both are different objects in memory, as you see on screen as well. So changes on one list won't affect the other list. Now, let's explore how to count and search elements in a list. We start by creating a list called nums. To count how many times the number 6 appears, we use the count method. This returns 2 since 6 appears twice in the list. It's the quickest way to find the frequency of any item in the list. Next, let's find the position of an element using the index method. Calling nums index 6 returns 1, the index of the first occurrence of 6. We can also search from a specific position. Nums index 6, 2 starts a search from index 2 and finds the next match at index 3. This helps when the same value appears multiple times in a list. Now, let's move on to sorting and reversing of a list. To sort the list in ascending order, we use the sort method, that is nums.sort. This arranges the elements from smallest to largest. The updated list becomes 36689. By default, sort modifies the original list in place. To sort the list in descending order, we use sort reverse equals to true. This arranges the elements from largest to smallest. The updated list is 98663. The reverse equals to true flag tells Python to sort in opposite direction. Finally, to reverse the order of elements, we use reverse method, that is nums.reverse. This flips the list from end to start. The updated list becomes 36689. It's a simple way to reverse the current order of items in place. Now, let's wrap up with nested lists and mixed data types. Python lists can hold different types of data in one place. Here we can create a mixed list of integers, strings, and floats all in one place. Accessing mix3 gives us the string ds, as you can see on the screen. This shows the flexibility of lists to store a combination of values. Now, let's look at nested lists, that is lists within a list. Here we can create a list with two inner lists, one with numbers and one with fruits. Accessing list 0 gives us the first inner list, that is 2, 4, 6. To get a specific item, we can chain indices. List 1, 1 returns kiwi. Nested lists help organize related data in a structured way. Now that we have explored how to create, modify, and access lists, let's take a quick look at the time complexities of these common operations. Let's break down the time complexity of common list operations in Python. Accessing an element by index is very fast. It takes constant time, that is O1. Appending items to the end of the list is also O1 on average, thanks to Python's dynamic resizing. That's amortized time. Inserting or deleting at the end follows the same, that is usually O1. But insertion or deletion at the start or middle takes longer, around ON, since elements need to shift. Searching through an unsorted list is also ON, as we may need to scan everything. If the list is sorted, we can use binary search, which brings it down to O of log n much faster. Understanding these complexities help you write code more efficient when working with lists. And that's pretty much everything for lists. Thanks a lot for watching, guys. If you found this helpful, don't forget to like the video and subscribe to the channel. Check out the links on the screen to watch more awesome content. See you in the next one. Keep learning, keep coding.